inspection, it appears that viscous liquid creates a different but equally horrific danger. It can spatter in small enough chunks that stick to surfaces, which if hot enough, can ignite. These early thicker fuels were clearly no solution, but they inspired Harry and the team to come up with a different approach to the same problem. If they couldn't stop the fuel from burning, they'd have to try and stop it from spilling. This meant designing a tank strong enough to contain the fuel in a crash, but still light enough for the plane to get up to gravity. The solution was a tough tank, a cut and tear-resistant bladder formed by a flexible mass. Unlike the rigid tanks, however, they could withstand greater impact force for longer by flexing and deforming, rather than rupturing under sudden violent pressure and distortion. The crash scientists set up another crash tank, with an aircraft containing two different kinds of tanks. One was the traditional rigid casing, built into the wing. The other was the bladder design. Sending the aircraft on the same collision course as before, they wait apprehensively for impact. The result is not what they hoped for. Both types of tanks rupture, and once again fuel and oil lines give way, and a fireball erupts. This plane doesn't even have full fuel tanks. In fact, just enough to run the test. The experiment highlights the severity and complexity of the problem. How do you prevent the wing fuel tanks in a large airliner from rupturing? And how do you contain the spillage in the event of a crash? In large airliners, the most efficient place to carry fuel is in the wings. But a large wing requires a thick metal skin, and when this breaks, even the toughest bladder tanks will be torn open. Harry and his team went on to solve the fuel spillage problem in smaller military aircraft, but the problem of fire persisted on larger commercial airliners. In 1985, one particular disaster highlighted the urgent need for a new approach. In Manchester, England, a plane carrying 131 holiday travelers caught fire just before takeoff. Firefighters were on the scene within minutes, but still 55 passengers died. Helen Muir, director of the Cranfield Institute for Safety in England, was determined to find out why so many people died.
The aircraft was taxiing down the runway, and the fire occurred in one of the engines, which caused the kerosene to catch fire within 2 minutes.
After showed the full horror of what passengers faced. Some of the materials inside the plane would have started to give off toxic fumes, turning the fuselage into a deadly gas chamber inside 2 minutes. These toxic gases can also explode in what's called a flashover, resulting in deadly temperature. Helen focused on what happened in the crucial minutes when there was still a chance of survival.
Well, the investigators checked some notes, and we knew that we had had 2 minutes with half the exit open. Still, 55 people hadn't got out, so the question was, why did we test the plane? We could get everybody out, or we really needed to. Sadly, we didn't.
This accident was, for crash scientists, a graphic illustration of the difference between a test and a real-life emergency.